so we're on slide 24 in the Nearpod. As you can imagine, we talked about gases, we talked about liquids, now we're talking about solids. Our goal is to describe the motion of particles in solids and the properties of solids according to the KMT, the kinetic molecular theory. We're going to talk about two types of solids, just give a basic introduction to crystal symmetry, and then look at the definitions, crystal structure, and unit cell. So again, with solids, particles are more closely packed than they would be in a liquid or a gas. The inner particle attractions exert stronger effects in solids, so therefore they stay closer together, and this causes the particles to be in relatively fixed positions. Solids are more ordered than liquids, and if you take Chem 2, we're going to learn about an idea called entropy. Entropy is kind of like chaos. It's how chaotic something is versus how orderly it is. So solids are less entropy because they're more ordered. There's two types of solids. We have crystalline solids and amorphous solids. Crystallines, like you would imagine, they are crystals that we are used to. They have a nice orderly geometric repeating pattern, whereas amorphous solids are arranged, the particles are arranged randomly. Amorphous meaning without shape, morph is shape, so amorphous is without shape. Solids do maintain a definite shape without a container, so if I put a rock in a beaker, it's not going to take the shape of the beaker, it's going to maintain its own shape. Crystals are geometrically regular, and I can change the volume of a solid slightly with a change of temperature or pressure. You're aware of this because sometimes you might have a door in your bedroom or the outside door where it gets really warm and then it starts to jam. It doesn't quite seem to fit right. That is because with temperature you have some expansion of solids, so the door frame might expand, the door might expand, and all the little mechanisms make it not work in an ideal way sometimes. Solid have a definite volume because their particles are packed closely together, unlike a liquid or a gas. So first, we're going to talk about melting point. Melting is the physical change of a solid to a liquid, as we know, as we see in the picture there, ice melting. And at that point, that temperature where a solid becomes liquid is the melting point. You guys know the melting point of water? So 100 would be the boiling point, so what would the other one be? To give you a hint, we're above. A melting point and the freezing point are going to be the same because it's like the opposite effect. So yeah, 0. And say we're at 24 degrees Celsius now. 0 is the melting point. So at this temperature, that's where you see the kinetic energies of the particles overcome the attractive forces. In the virtual lab, you see particles start to get the mind of their own. They start to escape the solid. So amorphous solids don't have a definite melting point. Things like glass and plastics, we see them as solid, but some of their properties are so close to liquids that sometimes they're called supercooled liquids. They appear to be solid, but they still maintain those certain liquid properties. And that's all because those particles inside the solid are arranged randomly. Another property of solids is that they have a very high density, and they're typically incompressible, meaning that substances are most dense when they are solid. Typically, we know that ice is an exception to that rule, but the higher the density results from the fact that particles are more closely packed. And we know that if I take a ball of aluminum foil, I can pretty much crinkle that up, but there comes a point where it becomes pretty incompressible. You can't really, if you get a ball of aluminum, you can't really squeeze it anymore. Once that air is all gone, the solid is pretty incompressible. You've seen, the solid chunks we've dealt with, like when we did the density lab. They're really hard. They're going to be really hard to compress because there's no air left in those. So solids for our practical purposes can be considered incompressible. Another thing you might not realize about solids is that they do diffuse. You will see different solids working their way through each other. This is what, you think of the earth layers and how they change over time. You have sand kind of rising to the top. Smaller particles will rise to the top of of solids, and this just happens at a slower rate because the particles are so close together. It's millions of times slower than you would expect diffusion to happen in liquids, but it does happen in solids. So let's talk about the crystalline solids. Like I said, they're groups of crystals fused together in a 3D arrangement. We call that a crystal structure. And that arrangement can be represented by what's called a lattice. Different crystals have different lattices. And the individual part of a lattice would be the unit cell. And on this next page, we have some examples of unit cells. We've got a simple cubic one here. This one is still cubic, but it's body-centered, so it has a molecule or a particle in the middle, and then the rest of those are still forming a cube. And then we have a little bit more complicated design there, a face-centric cubic. You can see how that shape would make a cube. But basically, these are all unit cells that we could build them together and make an entire crystal structure based on it, just like building blocks, just like. Don't get it confused with the animal cell and plant cell, but it's the same idea. We have lots of those together to build up a crystal lattice. If you remember our lab where we tested different ionic and covalent compounds, we knew that we could get maybe 4 to melt, but at some point, the 5th and 6th ones would not melt. They had too high of a melting point. And you can see, so like sodium chloride and magnesium fluoride, very, very high melting points, obviously very high boiling points. We're going to talk about this later, covalent network. Notice they have very high melting boiling points as well. Same with metallics. But then we have, as compared to covalent compounds like gases, ammonia, water, they have very low melting points because they happen to be water, happens to be liquid at room temperature. So ionic crystals, we've talked about these back in chapter 7. We have positive and negative ions arranged in a regular pattern. Typically, ionic crystals form with something from the left side of the periodic table, joins with something from the right side. So things like magnesium, calcium, sodium joining with fluorine, chlorine, even oxygen. And these crystals tend to be hard, brittle, high melting points, good insulators. Notice they're good insulators. They don't conduct well by themselves, but once you dissolve them in water, they tend to be good conductors. So I said I would talk about covalent network crystals. In these ones, every atom is covalently bonded to other neighboring atoms. So if you think back to when we built the models using the model kits, you had a carbon with 4 places to put other atoms. If you keep building that, carbons on carbons on carbons, you're eventually going to get this network crystal, a very strong kind of representation of different forms of carbon, which is why carbon, especially diamond, is very tough, it's very hard to break those bonds. So covalent network solids are very hard and brittle. They have high melting points, and they're usually non-conductors or semiconductors. Metallic crystals, we think of metals. We've talked about this before as well, where metals they just share their electrons. They don't have fixed electrons with each atom. The electrons belong to the crystal as a whole. So this allows metallic crystals to conduct electricity well. Finally, we have covalent molecular crystals. And these are covalently bonded molecules held together by intermolecular forces. So if we have nonpolar molecules, there's only weak London dispersion forces. But in polar covalent molecules, we have those crystals are held together by very, sometimes hydrogen bonds, stronger forces because of the polarity, the dipole-dipole forces. So sometimes in polar covalent molecular crystals, think things like, sugar. It's not an ionic bond, but it's a crystal, right? It's a molecular one. And sometimes those can be held together by hydrogen bonds even. And we saw that, right? Some of the solid crystals actually did melt in that ionic versus covalent lab. And finally, amorphous, I said finally already, but finally again, amorphous solids, that amorphous means without Greek, or without Greek for without shape. Unlike the atoms that form crystals, they're not arranged in a regular pattern. I already talked about that a little bit. Think of glass and plastic for amorphous solids. So in a solid, we have solid sodium there. Notice the particles are nice, evenly arrangements of there. In liquid, we melt the solid sodium a little bit, and now they start to move apart from one another. And finally, you see in this lamp, there's a gaseous sodium. So it's become such high energy that the particles can move freely apart from each other. And it's enclosed in that container, the light bulb. So that's all I had, just a brief summary of solids, crystalline and amorphous. We're going to go ahead and make some crystals here eventually. But there is that homework assignment that encompasses A through C. 1 through 3. It's homework 10A.